In today's video, we're going to be talking about analyzing motion with diagrams. After watching this video, you should be able to interpret a ticker tape diagram and be able to interpret vector diagrams. So let's get right into it. A ticker tape diagram basically is a diagram that's used to analyze the motion of an object. In particular, it's more in physics. I really haven't heard about this anywhere else in other courses. So basically the idea is as the object moves, it leaves a kind of pretend, if you will, trail of dots. So if you can imagine, let's say your car is leaking oil and there's a trail of dots that are left behind your car as it travels. The trail of dots actually provides a history of your car's motion. So as the distance between the dots on a ticker tape diagram does actually represent the object's positional change. Okay, so if the dots are really far apart, it means the object must be moving really fast. So here's an example of one right here. There's two of them. This one on top, the object must be moving really fast. How do I know that? Well, it's because these dots are really far apart from one another. Okay, so the object must have traveled a large distance before the drop of oil fell again and hit the ground. Whereas below here in this one, you notice the dots are relatively close together. And so relatively speaking, this object must be moving slow, or at least slower than, say, the above ticker tape diagram. Okay, so it's just basically kind of like a trail that's left behind, and by using that trail you can actually determine qualitatively how fast an object is moving. Okay, there's not so much of a numerical value associated with it. It's just basically saying, yeah, it's moving really fast, or it's moving slow, it's either speeding up or it's slowing down, that type of thing. So ticker tapes tell you the velocity of the object, and it'll tell you if the object is accelerating. So let's do an example of this. Here is a ticker tape diagram, and here's some dots. And I guess we could say, hey, this thing is moving relatively fast because the dots are pretty far apart. Okay, so it has a fast velocity. Okay, it's moving pretty quickly. Now, is the object accelerating? Okay, and now remember, an acceleration means a change in velocity. An acceleration means a change in velocity. So do you feel like the velocity is changing at all when you look at these dots? And I would say no. I mean, I didn't measure these perfectly, but these dots are about equal distance from one another. So there is no acceleration present. Okay, and so basically the velocity is staying constant. Okay, it's moving at the same speed. Let's take a look at another ticker tape diagram down here. Let's say I have some dots here, and you can see that basically it starts off, this object, whatever it is, starts off relatively slow over here because the dots are pretty close together, but as it moves and progresses from left to right, all of a sudden you can start seeing, man, it's really starting to go fast over here. Is there a change in acceleration? Absolutely, right? The velocity is changing, so there is a change in acceleration. And so this is basically what a ticker tape diagram can provide. It's just some information telling you whether or not an object is speeding up, slowing down, keeping the same velocity. Is it moving relatively fast? Is it moving relatively slow? And you're just basically using these dots to kind of give you an idea of what's happening. And that's called a ticker tape diagram. It's kind of hard to say fast, but you certainly can try. The second type of diagram that represents motion is something called a vector diagram. And these vector diagrams basically depict the direction and magnitude of a vector quantity by using an arrow. Okay, so it's done by using an arrow. Once again, it is totally qualitative. There's really not a numerical value associated with it. Typically, you're saying, oh, that one's faster or slower, or it's moving in this direction or that direction. You don't have like the number associated with it. So in a vector diagram, the magnitude of a vector quantity is represented by the size of the arrow. Okay, so as the arrow gets bigger, the velocity, if we're talking about velocity, increases. As it gets smaller, the velocity decreases. And that would be true of any, basically any vector quantity that we would talk about in this class. So I list some examples down here. Vector arrows can be used to represent many quantities such as acceleration, force and momentum. We could put velocity in that list if you want to too, because velocity clearly is a vector. That's something we've talked about in previous lessons. Okay, so so far we've talked about ticker tape diagrams, and now it kind of introduces this new thing called a vector diagram, which is basically just using an arrow. The arrow indicates the direction, and the size of the arrow indicates the magnitude, the numerical value, if you will, even though you're not really using a number. So let's do a little bit of an example here. All my examples are going to be dealing with force. Okay, so force is a vector. Okay, it is a vector, so it will have a direction and a magnitude associated with it. And let's say I draw an arrow like this, and let's say I draw an arrow like this. Okay, so in this example, which of these arrows is which of these arrows, yes, is the bigger force? Well, hopefully you can say that this one here, because it's longer, is a big force, and this one over here, oh, it's a relatively small force. You also could put a directional piece here. If we're saying north is up, south is down, east is right, and west is left, we could say both of these forces are pushing to the east. Okay. Another example could be let's say I change a direction on you. Let's say I have an arrow pointing here, and let's say I have an arrow pointing here. All right. Once again, you could say that this is a small force, okay, because it's a tiny arrow, and this is a big force. And we could even go into saying the direction, because we should, that it is a vector, and so we could say that this is headed north. The force is pushing north, and this force is pushing south. Okay. Another interesting thing that can be done is if we look at, say, like velocity and acceleration. Okay, and this may get a little confusing, but I don't think it'd be anything horrible. Let's say you have a car, and this car has a velocity that's going to the right, and it has an acceleration to the left. What does that mean the car is actually doing? Right? Well, if it's traveling to the right with some velocity, okay, and it's accelerating to the left, that means that it's actually slowing down, okay? And again, we can't really put a numerical value on it, like how much is it slowing down or what was its velocity, but we can kind of, if you see something like this, you can say, well, it is traveling to the right, yes, but it's traveling to the right and it's slowing down as it travels to the right, because this would be my velocity arrow, the top one, and this would be my acceleration arrow, which is the bottom one. So I don't think it's anything too horrible. Once you kind of get a feel for it, it might seem a little weird because typically we don't represent things with arrows and dots, but that's kind of one of the ways that we can represent motion in physics. That actually takes care of this video. I will see you guys next time.